So far, we have investigated vacuum or space filled completely with materials. To analyze layered structures, we need to take materials boundaries into account. For this, we need to consider boundary conditions of electric and magnetic fields and polarization. Our next task is to determine reflection and transmission of plane waves at interfaces. This is also repetition from basic courses, but I'm using some specific notations, especially for this course. To begin with, I would like to introduce the boundary conditions and wave vectors. Boundary conditions are formally written as unit vector of the normal of the interface is pointing towards the incident field. This means that tangential field of the electric field is continuous across the interface. Also, the tangential component of the magnetic field is continuous across the interface. Next, the wave vectors and numbers. We can separate the wave vector of free space into its normal and tangential component. Due to the boundary conditions, the tangential component of the wave vector is also continuous across the interface. The normal component can be different, and this results in refraction of the plane wave. Continuity of the tangential wave vector will play a significant role in various aspects of the topics that we encounter later. Once more, the tangential component is continuous, and this condition we know as the Snell's law. Finally, we consider polarization. Polarization of the plane wave is defined by the vector direction of its electric field. It is defined with respect to the boundary and the plane of incidence. The plane of incidence in this case is the plane of the flat screen. Two linear polarizations are usually defined. The first is the so-called transverse electric polarization, or TE, or S polarization, where the electric field is perpendicular and the magnetic field is on plane. The other polarization is the transverse magnetic, TM, or P polarization. In this case, the magnetic field is perpendicular to the plane and the electric field is on plane. Basically, all the other polarizations can be defined by linear combinations of these two polarizations. We shall see that the reflection and transmission properties depend strongly on polarization of the plane wave.